Okay, so you understand it. Okay, now there's a proof. Last time we did group velocity. There's a proof that the group velocity is less than c if the following conditions hold. First of all, epsilon minus 1 has to go to 0 as fast as 1 over omega squared. That's so that turned out so that you can so that certain contour integral will converge will go to 0 at infinity. We'll see why in a minute. And the other is that the medium is stable.
What integral?
We'll see. The other, the medium is stable. And do I have the proof here?
B group is always less than C, right?
Yeah, can you prove it?
If I can prove it, I don't know.
How do you prove it?
Not
What?
in the medium.
What?
In the medium also.
In the medium you just
Because group
Do the
velocity carries information,
yeah, but
and you can't send information faster than the speed of light.
Why that?
Why is that?
Yes. Information.
I don't know.
I understand
that's
about the message.
That's
I
the way
understand.
the universe was made.
No.
you
Can we-
just lose energy to the radiation.
What Einstein
Yes. What
Einstein started general special relativity with the proposition of causality. You can't violate causality in special relativity. No.
But I know. But
Although, how do you
How-
prove it?
how do I evaluate with this causality? If
You
big
could,
group-
if the group velocity would be greater than c,
okay.
unless the dispersion is ridiculously fast. Then you could send the message faster than c using a wave pulse.
Okay. I can send message. Okay. Okay. Makes sense.
Yeah,
You
but-
could send the message back to a time before you were born, as seen by some observer. That instructs your grandmother to kill your grandfather,
Okay.
and that's not allowed
But you can send a particle into a medium.
because you aren't born yet. Yeah,
you can send it. It's like that movie.
Back to the Future.
Yeah.
Yeah.
Right.
You can send a particle into a medium with velocity higher than the speed velocity in that one. You get just
And that's called Cherenkov radiation.
Yeah, exactly. And I think that
But that's the-
someone tried to prove it for vacuum. And nobody in vacuum.
He proved, Sonneveld proved that the signal velocity cannot go faster than c. Signal velocity being the leading edge of the wave packet. If it's exactly 0 and then suddenly it's non-zero, then there's the non-analyticity. Anyway, he proved that the first non-zero point, or the last 0 point, moves at most at c. So you can't violate causality. In some sense, this is not surprising. What's surprising is that you can prove it mathematically.
So yes,
But-
mathematically, I don't think. Have you seen ever proof of this?
Yeah, it's in Landau and Lifshitz.
Okay.
Theory, electrodynamics of continuous media. Now the significance of this is that there are a finite number of oscillators. Any given oscillator in the limit of high omega, the polarization goes as 1 over omega squared, because as a finite plasma frequency. If there are an infinite number of different species of oscillators, it's like an infinite medium, then that doesn't necessarily apply. And the other is that the medium is stable, which means that I'm sure I taught this, so maybe we'll get to it later in the course, this proof. In fact, maybe later in this week. I just have to do electrostatic waves first, but when we start talking about instabilities, you'll see the consequences of why we need to assume the medium is stable to prove that the group velocity is less than c.
That's a question. I don't understand why is that possible to have a particle coming with a group velocity greater than c if it's possible inside a medium, and then you get the radiation.
Who said it's possible inside a medium?
Yeah, you can send a particle with
You said faster than the speed of light in the medium.
In the medium.
But the speed of light in the medium is not c, it's c over square root of epsilon.
Yeah, over epsilon. Yeah. So this is why I'm asking, is it not possible to also have it in vacuum and just the energy lost to radiation in the same sense?
No, it's not possible.
Why?
Because, first of all, the vacuum is stable.
Yeah.
And secondly, because epsilon minus 1 is 0. And which goes to 0 goes to 0 at least as fast as 1 over omega squared. So anyway, the phase velocity and the group velocity in the vacuum is the speed of light. Now it's true that that's not really true, what I just said. In vacuum, the phase velocity and the group velocity are both the speed of light, but it's not true that epsilon is always equal to 1 in the vacuum, because when you start talking about fancy vacuum fluctuations and renormalization, then it turns out that in the vacuum epsilon can be different from 1. It's just that epsilon times mu, which if you really do Maxwell's equations carefully and you include the magnetic susceptibility of the medium, the speed of light is not 1 over square root of epsilon, it's 1 over square root of epsilon mu, where mu is the magnetic permeability or susceptibility, I don't even remember. And it's the product of the two that has to be 1. So it's always the speed of light in vacuum, because vacuum is by definition Lorentz invariant. But you can have funny renormalization effects that make epsilon and mu different, and that's why you get renormalization of charge and flux tubes in the vacuum. But that's fancy field theory, and for us the vacuum is empty. When I say vacuum here, I mean epsilon is equal to 1 in this course. Anyway, the way to prove this is to is to show that maybe I don't prove it in this course. Maybe I prove something a little different in this course related to causality. The point is that if you write epsilon, the Fourier transform of epsilon is a function of k over and omega, epsilon is really a function of x and t. In other words, the electric field at any point, the polarization at any point is a function of the electric field, not at that instant, which is what we've assumed up until now, but it's also a function of past history of the electric field. So far we've just been doing electrostatics, which is not really no, we weren't doing electrostatics, but we assumed that the electrons were cold, and we neglected the transient solution. And in calculating the response of the electrons to an electric field, and we will continue to do that. But the justification for doing that, for throwing away the transient solution, is the assumption that the medium is stable and that the initial conditions die out instead of grow. That's the significance of stability. So actually, until now we've been assuming that the medium was stable, because in calculating x of t of the electron in response to the electric field, we neglected the initial conditions. And also we assumed a finite number of species, so this assumption was always true for R epsilon. And it's hard to see how it could not be true, because just mathematically you could imagine having an infinite number of species, but it's not physical. And with a finite number of species, the species with the highest plasma frequency will be the one that dominates after, for omega bigger than that highest plasma frequency, and then the polarization goes as omega p squared over omega squared. So it certainly goes as fast as 1 over omega squared. Okay, now I did electromagnetic waves, very low frequencies, high frequencies, intermediate frequencies, but now there's electrostatic waves, and you also have to solve this equation, and that means you have to calculate what rho is, what the charge density is, which means you have to calculate the motion of the electrons. Well, you always did that, but when k was perpendicular to x, and E was perpendicular to K, when E was perpendicular to K is when K dot E was 0, and there was no charge density associated with purely electromagnetic waves. For electrostatic waves, you have to calculate rho. Now, this equation is implicit in this equation, because when you take the divergence of a curl, the left-hand side has to be 0. It's actually this equation. If I take the divergence of this equation, it's this. The divergence of a curl is 0, so the left-hand side is 0, and then this is. No. This proves that the time derivative of div B is equal to 0, which means that you can't create a magnetic monopole. So that's basically conservation of magnetic charge. Conservation of electric charge comes from this. You take the divergence of this term, so the left-hand side is 0. The right-hand side is the divergence of J, which is d rho dt. Right? If I take the divergence of this equation, okay, so the left-hand side is 0, the right-hand side is 4 pi over c div J, plus d dt c. Okay, now the divergence of J is d rho dt. That's just what. That's conservation of charge.
Okay. And this is rho.
And this is 1 over c d dt. So d dt of div e minus 4 pi rho is equal to 0. This follows from this. So
Again, what follows from what?
This
Yes.
follows from this, which follows from this, which follows from this. So this follows from this.
Oh, okay.
But this is the time derivative of this equation. So if this is true at one instant, if this equation is obeyed at one instant, then it has to be obeyed at all other instants. So really, the only new information here is that it's 0 at least one instant, and then the rest follows from this equation.
Okay.
So again, if this is true initially, then it's true at all other times. Now, electrostatic waves have k, at least one component of V parallel to k. So k is a single direction, so you don't have circularly polarized electrostatic modes per se with a given k.
You said the divergence of V is equal to rho follows from another Maxwell equation?
I said that the time derivative of this equation follows from this equation.
Yeah.
Okay. So if B is 0, we already calculated this. You did it for homework, I think, right?
Okay, yeah.
For B non-zero, now we have to categorize things. First we take E parallel to X and B parallel to Z, where K is in the X direction.
Okay.
So if E is in the X direction, it means particle motion is in the X direction, and if B is in the Z direction, you'll get acceleration in the Y direction. So you have to include the Y dot, which is the component of Vy cross. It's the X component of Vy cross B. Because B's in the Z direction.
Mm-hmm.
So X double dot is equal to the electric force plus the V cross B over C force. And this, of course, should have a C in it. But I'm going to assume that C is equal to 1, probably. It's a lot easier.
Why is that equal to minus 1?
What?
Why is that equal to minus 1?
Because I'm assuming that X has e to the I kx minus omega t dependence. So double dot means minus omega squared. E to the, excuse me, the I should be multiplying mu minus omega t. Okay? Second derivative here. X is equal to when you have e to I omega t dependence, time derivative is just I omega, right?
It's dependent.
Alright, and y double dot is just since E is in the x direction, it's just the Vx cross Bz term. And this is minus I omega y double dot. So this gives a relation between y double dot and x double dot. Okay, and then the top equation can be rewritten this way, and I get that x is equal to this. Now what? Conservation of charge imposes a constraint. So this is the density fluctuation, basically, for different species, and this is the density without fluctuation, n0, and it's proportional to the electric field, which you expect. They're both first order quantities. Poisson's equation tells you this.
You don't take n as a function of the space?
Nope. N1 is perturbed quantity is, but N0 is assumed to be constant in space.
Why do you make this assumption that in this part you take okay, it's first order and you add these two.
Alright, so Poisson's equation implies this. And therefore, this equation, this mode corresponds to, it's called the upper hybrid mode. When there's no magnetic field, it just corresponds to plasma oscillations. It's the usual Langmuir, what's called Langmuir wave. When you add the magnetic field, you have an extra restoring force if it tries to oscillate, because it gyrates, and the magnetic field helps restore the charge density.
What about
By the way, if omega plasma is zero, if you just have a very dilute gas of test particles, and omega cyclotron is much bigger than omega plasma, then it's just a cyclotron. It's just everything goes at the cyclotron frequency. It's just because it's just density fluctuations caused by cyclotron gyration. If I initially had stripes and everything gyrated, it would come back to where it was after one gyration period. So it would look like oscillations, but not because the guiding centers were moving, but just because everything is coming back to where it started. So when the initial fluctuation comes back to haunt you every gyro period. And that's what's called a cyclotron wave. And it just happens to have essentially almost zero group velocity, because omega is just the cyclotron frequency. It doesn't depend on K very much. Anyway, epsilon is now this. And that's an upper hybrid wave. Now at this point, for some reason, I decided to do a formal review of the epsilon tensor, at least in 2 dimensions. And this is the equation you get basically the eigenvalue equation you get. Now, I don't know why they're called M modes. That's a misprint. Generally speaking, there are ordinary modes and extraordinary modes. And the ordinary mode is when the magnetic field does not affect the oscillation of the electron. In other words, the electron moves parallel to the magnetic field. In the extraordinary mode, the magnetic field affects the dispersion relation, which is why it's called extraordinary. And ordinary mode is sometimes called O mode. Extraordinary mode is then called X mode. So you hear about the O mode and the X mode. It's the extraordinary and the extraordinary mode. I have no idea what M modes means. I have to look up my handwritten notes.
What is gamma vector?
What is what?
Gamma vector.
I don't know what a gamma. It's not gamma. I think it's R. And she typed it wrong. It's the it looks like the amount of polarization times the charge. It looks like the polarization vector, 1 plus 4 pi p. You turn the air conditioner. What's the temperature at? 25, 26, that's good. Well, if you believe this, then I'm substituting this quantity in for this quantity into this equation, and then I get this. And now this is an eigenvalue. I have to find the eigenmodes for Ex and Ey. For some reason, I'm trying this. But since epsilon is a tensor, there are three directions here. First of all, there's the zeroth order magnetic field direction, and then there's the k vector direction, and then there's the polarization direction of the wave electromagnetic field, and the relative phases of the x and y components. So, generally speaking, you have to immediately divide things into four cases. If you do things all very generally, you get a big expression for epsilon in all three dimensions, and you have no intuition. The idea is to consider limiting cases, so you at least develop some intuition. Now, the first thing we did is we considered, well, first of all, if you have three directions, after you pick the first one, the other two you can pick parallel to the first one or perpendicular to the first one. So immediately you have four possibilities. Let's say you pick B first. So you pick B naught first. Now you have to decide the k vector could either be parallel to B or perpendicular to B. Those are the two extreme cases. And then the electric field can either be parallel to K,
It cannot be perpendicular. You have three cases.
yeah. See, why do you argue with everything? Let me
No, no,
finish.
no.
Let me finish, and then you can argue. If you pick B, you can pick K perpendicular to B or parallel to B. If you pick K parallel to B, you can pick E parallel to both of them or E perpendicular to both of them. Now if you pick K perpendicular to B, you can still have E parallel to K and perpendicular to B, or E parallel to B and perpendicular to K, or you can have E perpendicular to both of them. So that's three possibilities just for K perpendicular to B. And those are four altogether, right? For K parallel to B, I still had two possibilities. So sorry, it's five because I had an electrostatic mode where E is parallel to K and B, and electromagnetic mode where E is perpendicular to both K and B. And when when K is perpendicular to B, I can pick E in any one of three directions, and I get a different case. So the first two cases were just electromagnetic and electrostatic modes propagating parallel to B. That's when K was parallel to B. When K is perpendicular to B, I can have an ordinary mode, an ordinary electromagnetic mode, or an extraordinary electromagnetic mode, which is when E is perpendicular to both K and B. And I can have an electrostatic mode, which is when E is parallel to K. So last time I did, after I did electromagnetic K parallel to B, I did electromagnetic modes for K perpendicular to B, and I did the extraordinary mode, the O mode and the X mode, right? Let's go back. We might as well go back and review. This was still electromagnetic mode, but then I went right here. At this point, I started K perpendicular to B naught, and I should have had like a whole new heading here. And then we start with the ordinary mode, and that's easy. The B naught has no effect. It was just what we did before, without B. Then the extraordinary mode, and it's not purely electromagnetic. So after discussing group velocity, which is totally out of place, it was a mistake that I got here. I go back to doing the extraordinary mode. Hello?
Hi,
Yeah, I'll talk to her tonight. I'm in the middle of the class. Right. Yeah, he found me. Alright, now I'm back to O modes and X modes. And electrostatic waves. So first I pick E parallel to X, B perpendicular to Z. So E is perpendicular to B. So this is going to be which mode? If it's electromagnetic, it's going to... The perturbed E is perpendicular to the zeroth order. This should be B naught.
Which direction is K?
K is in the X direction because well, I didn't say that yet, but eventually I'll say that K is in the X direction. Where was I? Yeah. Well, you know, if K is in the X direction, then it's parallel to E, and it's in electrostatic mode. And if it's parallel to, well, we said it's perpendicular to B, but if it's also perpendicular to E, then it's in electromagnetic mode. But which electromagnetic mode? It's the X mode because we're considering motion across B fields now. So there's Y velocity and X velocity, and the magnetic field is entering into the equations of motion for the charged particles, and that means it's the extraordinary mode if it's an electromagnetic mode. Or if it's even if it's an electrostatic mode, because K is perpendicular to B. So the point is, I get this equation. I get that. I get that epsilon. Here I assume. By the way, here B is always B naught. I assume this E is in the X direction, and I get this polarization vector. And if I invoke Poisson's equation for an electrostatic mode, I get this. This is what I did before. This is for an upper hybrid electrostatic mode, but it's also Okay, this is for an electrostatic mode, but the point is, the discussion could be a little more general, and that's what I do here. I treat epsilon as a tensor, and I get this matrix equation for epsilon. I don't yet know what epsilon is. I just have this matrix equation, which is basically a matrix form of rewriting these individual equations for the acceleration in the x and y directions of the electrons. So I have to solve this equation, and that's basically what plasma waves is all about. It's solving this equation. Now, I don't know why I said Ex and Ey. Ignore these things that are circled. I had some reason for putting them in, but I have no idea why. So just focus on this equation. This is a matrix equation for epsilon, and it basically tells you that epsilon is equal to 1 plus this. I mean, it tells you what epsilon is, but the point is now you have to solve for the eigenvalues of epsilon to find the modes. That's what plasma wave theory is all about, finding the eigenmodes for epsilon.
Isn't this just a way of writing that vector in matrix form?
What?
The first circle thing, right-handed vector. It's just a way of writing column vector. 1 I and 1 minus I.
Yes, but why specifically did I pick these two forms?
One is the right-handed and
Yeah, but I don't think that those. In this particular case, I don't think that these are the eigenmodes for epsilon. So I don't know. I mean, they're not. Look. Wait a minute. Wait, maybe they are. It certainly seems that they are eigenmodes. But why? Why is that? Why are the circular polarizations?
I think it was
Oh, I see. Maybe there was an E here? Electromagnetic modes? Is it hiding behind? It can't
No,
be. Maybe you just cut it off.
Yeah, maybe it's probably copy paste. So it was cut off.
Okay. So this is.
Yeah.
so it has nothing
Okay,
to
so
do-
so these are electromagnetic modes. K. The thing is, could it be that it doesn't depend on K? Yeah, I guess it. These equations of motions didn't care about what K was because they were happening at each point separately. So yeah, okay, mystery solved. I wrote it this way because these are the eigenmodes for epsilon. Hang on, guys. I'm learning something today. It means even if k is in the direction of E, I still have to consider two waves.
Saying later on you wrote electrostatic k parallel to x. That's like.
That's
K,
right.
That's k in the.
That's k in the E direction. And then I got this. You don't have to know this yet just to get this. You can solve it for this. But here's the thing. I'm not getting this as the mode. I'm looking at this equation. Oh, I see. Oh, I see. I can look at a linearly polarized mode, which is what this is. If E is if it's purely electrostatic mode, I'm thinking E has to be in the x direction. And what's this EY being I times EX? I mean, there isn't any EY. But another way to say that is simply that the mode here is a superposition of two circularly polarized modes. But does that mean? But maybe it doesn't. Excuse me. Okay, I'm glad. This is what equations are for, because after a year or two, I forget it, and then I'm reminded. What I had in mind here was to neglect EY. In other words, if EY is small compared to EX, then the top equation is okay, this is what I get from Maxwell's equations. Assuming the k is parallel to the x direction. Alright. Now, a priori, this equation is not easy. First of all, it's two separate equations. And I think the notes here are just a little bit too terse.
I think that's okay. You assume the EY is very small compared to EX.
I'm looking for a solution where EY is very small compared to EX.
Yeah, and then you have solution.
But you see here, in the eigenmodes, they were not. EY was not small compared to EX. It was just out of phase. So I'm just wondering, now what's bothering me...
You can solve this.
No, yeah, you can solve it. you can solve it approximately, but really, if you wanted to solve it exactly, you would solve for both eigenmodes separately. And but they wouldn't be eigenmodes. That's what's bothering me. They'd be eigenmodes for epsilon, but not for this equation, which has, it's more than just a definition of epsilon. This is Maxwell's equation. It has to satisfy this. And the eigenmodes of epsilon don't satisfy Maxwell's equations exactly. I think that's what's bothering me here. So
Maybe it's because of that you assume EY is missing.
yeah, so the point is, I'm looking for something to simplify my life. That's the point. Because generally speaking, plasma waves are more complicated than any normal person would like them to be. So you look for limits and simplifying. So let's just look for a wave where EY is much less than EX. And that's just because of initial conditions. I could have assumed that EX was much less than EY, and I would have gotten the same thing. But if EY is much less than EX, then I can ignore EY in this equation, in the top equation, and I just get 1 minus omega p squared, omega minus, is equal to 1 times EX plus I omega big over omega small times EY. But since I'm neglecting EY, then I'm saying this: the top left-hand side has to equal the top right-hand side, which is 0. Everybody get that?
Can you say it again? Please?
Yeah. Okay. First of all, it's an approximation.
Okay.
I'm neglecting EY.
Okay.
If I neglect EY, then I get the top left-hand, the left-hand side of the top equation, namely the equation for EX, is equal to this, which is
Right.
0.
Okay.
So that's essentially saying that this is 0. But only because I'm neglecting this term, capital omega over small omega EY.
Oh, okay.
And now why am I neglecting it? Because I'm looking for a solution where I can neglect it.
Right.
I can't always neglect it, but I'm just saying, let's just say that I can neglect it. So then I get this equation, which gives me a dispersion equation. It's omega squared is equal to omega p squared plus omega cyclotron squared. And this,
Can I ask a question?
Shouldn't
Maybe I missed
if
something.
it's a single species. Yeah, you can ask it as soon as I finish my sentence. I promise. Yeah. So this is true as long as I can really neglect EY. Okay.
Maybe I missed something, but we didn't take the electric field only in the x direction?
At first we did. And we got the same thing. We got this when we took the electric field in the x direction. But now I'm doing it a little bit more generally. I'm writing it. I'm taking it in the x direction at the end instead of at the beginning. That's the only difference. And I'm saying that it's really not an eigenmode exactly. It's only an approximate eigenmode. And I have to make sure the EY really is less than EX. In order to justify taking E in the X direction, I have to, because they're not totally decoupled. If I have EX, I have to have a little bit of EY, and the only question is, when is it small enough to be negligible?
I'm a little confused here.
Yeah.
When you neglect EY,
Yeah.
and you should have here EX, right? In
This
this
better be
equation.
good. Hello?
כן, אבל אז תזרוק אותו בחוץ.
איך, אבל זה אחד זה בלי X.
לא, כל זה עם X.
No, together.
זה סוגריים.
This whole thing is
Okay.
on this vector
Yeah, yes.
with 1.
Hello?
איך אתה
זה
יודע?
סוגריים.
Hello?
נכון, חייב להיות.
כי גם אם זה כן,
What-
אבל
what do they
זה
want?
X, זה 1, X, EY.
כאילו, אחד זה אין שם.
זה game equality.
Thanks. Okay. You happy?
Yeah.
Okay. Now, here's the thing. If you move something across the magnetic field, and you have charge separation across the magnetic field, the magnetic field can cause rotation. I mean, it can make things that were initially moving in the X direction move in the Y direction. So it can rotate the polarization vector. Just the presence of a magnetic field and charges that are going like this, eventually they'll start going like this and around, and So when can I ignore that? I can only ignore that if the reversal of the electric field is fast compared to the rate at which the magnetic field will cause them to gyrate. So the point is, I can only do that when omega is large enough, which means that this is only valid when omega is large enough,
It doesn't.
and that's why it's called the upper hybrid wave.
It's opposite.
What?
The very large. It's supposed to be very small.
Yeah, it's גדול.
All right. Let's see mathematically what it is. I have to satisfy the bottom equation. I agree with you. This is probably
Because if you want to correct from this equation, omega squared.
a misprint, but let's see if we can decide it just mathematically. What? Since it has a c squared, k squared, omega squared, and if the bottom equation is 0, just like the top equation, then this would satisfy Okay, let's see. Well, one thing we could do is we could solve the matrix equation.
We divide by EY in the second equation.
right? Then I'll have an e. The problem is I'll have an ex over ey.
Maybe divide by
And
ex, then
well, here's the thing: if this is equal to 0, then 1 minus. If this is true, then the bottom left-hand side of the equation is minus omega p squared over omega squared minus ey. Right, because 1 minus this, I subtract out the 1 here. No. No.
I think that's true. If it's not very large, then on the right hand side you will have something very close to 0. And that means ex should also be very small. You write just second equation from the matrix.
Well, it's omega over omega times ex has to be very
So
small.
let's say if you know ey, then right hand side, if the c squared k squared omega squared is small, then
If I'm ignoring ey, then every time I see
everything
ey.
becomes very everything
Well,
becomes-
no, because if I'm canceling out
No, I'm saying if this condition is not satisfied, then it implies the ex is also very small.
just a second. This thing is a. No, I'm sorry. I can't. First of all, these ones have to stay because they're being multiplied by this. Yeah. So I want to write the bottom. I want to write the bottom equation. Let's just write it out. Okay. So we get we get 1 minus omega p squared, omega squared minus squared ey minus ey. Come on, ey. Minus, I have to multiply this term omega squared over omega squared minus omega squared. And here's a minus. Okay, that's this term times ex. And this is equal to c squared k squared over omega squared ey. Now, what do we want to do? We want to show that ey is in order to we actually had to neglect omega, big omega over little omega times ey. That was the term we neglected the first time around. So the real question is, when is ey much less than, when is omega over omega much less than ex? Okay, so
simply divide this with
So that would mean that would also mean that if this is true, then it would also mean that omega squared is much less than right? I just multiplied by omega, big omega over little omega. If this is true, then this is true. But this term here is this term here. What time is it?
13 minutes.
Well, we could spend 13 minutes trying to figure out why this is true.
It's true or
We could figure that out too.
because I think about it from this equation. Usually you have the omega c square omega c square k square. No, you don't have it. Meaning it's much smaller than this.
Could be. If this was much less than 1, but the point is this is also much less than 1 because I assume that it was roughly 0 for the electrostatic mode. Okay, here's the point. Here's the point. I can always make this small by making k small. See, omega is going to a constant, even at small k. So I can always make this small when k is small. I just have to choose k small enough. And what does k very small mean? It means it's essentially it's almost an electrostatic mode. If k is exactly 0, never mind that. Let's just move on. I for homework you can solve this. You can just solve this equation, using linear algebra. And
looks like if you divide by EX in the equation,
divide by EX, yeah.
and you demand basically EY over EX is very small. this condition you want now.
If ey over ex is very small, that means I neglect this term and I have only this term.
So which is now to only see.
So I would need that omega has to be much bigger than omega cyclotron, which is sort of what I was arguing before. That in order for this equation to hold, I can't have one term much bigger than the other two. That's for sure. If these two terms were much bigger than this, then maybe. But I certainly cannot have this term be much bigger than this term. And since omega squared over omega squared minus big omega squared is roughly 1, I can't say it's small because of this. I have to say it's small because of this. So omega. So certainly a necessary condition is that omega has to be much greater than omega. For this to be true. Now maybe this also has to be true, but this certainly has to be true. Now, it could be that this also has to be true.
Wait, this is on the magnetic field.
What?
If omega squared is equal to this,
Yeah.
it needs to be dependent on the magnetic field if it's big enough or not. Because omega p is constant. Omega is dependent on the magnetic field.
If this is equal to this, then this is 0, okay? This is roughly 0. Now, I could have, in principle, I could have, and this is roughly 1, so in principle I could have a situation where this term is equal to this term.
Oh, right, it's from there.
Yeah, let's assume that this term is equal to this term, then this term has to be much greater than this term. So it's C, right? Because this is 0, this is roughly EY is much smaller than EX, but these two terms have to be equal, which means that this coefficient has to be much greater than this coefficient. So I think what I meant to write was this. And therefore, if I write this, I can cross this out here, right? And I can cross this out and make it 1. So maybe that's what I meant to do, is to just now it's also true that since this is I guess easier to satisfy. No, wait a minute. Wait. No, I'm sorry. This is omega squared and this is omega p squared. So this is avoid a unity. And for EY to be much less than EX, then this has to be much greater than this, yeah. So that's this, right?
How do you get this omega square over omega square minus big omega? Is the 1 minus omega p square in the whole? Things are typed in the matrix earlier.
Oh, you're right. This should be an omega p.
Also 1 minus it.
What?
This 1 minus is on the whole. Whole matrix is multiplied by 1 minus it. Or not, I don't know.
No, this one is diagonal element, right?
Okay.
And it's the bottom equation. So it was
So it's omega.
it was just this coefficient times this matrix element. Well, sorry, times this matrix element. So yes, so this is a Vorti. Wait a minute, but now let me redo this. This we said was
Yeah, that's right. This is
roughly
one.
0.
No, it's
No,
one.
this is a Vorta 1. Yeah,
It's exactly one.
yeah, it's exactly 1. No, oh yeah, it's exactly 1, and therefore yeah. So I'm going with this.
So C square.
But now the question is, do I really need this? What if omega? What if this is much bigger than this? This is still 0. This is still 1.
So approximately big omega.
So this. Do as long as I satisfy this, do I really need this?
No.
No, I think I do.
Few.
I think I do.
Now
Because then this would.
let's say big omega and small omega are comparable, and if you
Yeah.
divide everything by ex, and then the right hand side you get ey over ex, which is very small,
Yeah.
multiplied by c square k square divided by omega square.
Yeah.
And let's say if big omega over and omega are comparable, that's finite.
Yeah.
So in order for the right hand to be finite, c square k square over omega square should be very large.
That's right.
And
Larger than what?
Then what?
It should
Of
be.
the same order of-
This should be larger than this, basically,
Yeah.
and that's
Same
what
order.
this says.
Yes.
But therefore, I don't need this.
Yes.
It's so this was actually almost right. And the thing is, if the original would have been right too, because when this is small compared to omega p, then if omega squared would be 1 over omega squared would be even smaller, so this would be even more true than the other one.
No. If omega is
Anyway,
much
it
smaller
doesn't
than
matter.
omega-
I think you certainly need this to be true. This is a necessary condition. Whether it's a sufficient condition depends on how small you want EY to be. So let's leave it at that. Okay. For lower hybrid, that's when this is no longer true. but lower hybrid, you have to consider two ion species, and you have to consider quasi-neutrality. So epsilon, so the polarization vector is basically zero. And since the polarization vector for the two species is just given by this, where this is for the electrons and this is for the ions, then quasi-neutrality means you just set x equal to xi, which means this equals this, and the obviously little e times big E cancels out, and just the denominators have to be equal, and you immediately get that let's just say that omega, the real omega, is between, much less than this and much less than this. It means I can neglect omega on the left-hand side. On the right-hand side, I can neglect omega I, and then it means I get this, and it means that I get omega is just the geometric mean of the two gyrated, and that is the dispersion relation for lower hybrid waves. In case you ever hear lower hybrid waves, you know what it is. And then the one more thing is ion cyclotron, which is when omega is below, well, it's when this is no longer true, and then you find that it's about equal to omega. It's just ion cyclotron.
What is it for?
It's small number. Let's say delta. Okay. You know what? Yeah. I'll finish this tonight.
יש סוגיות גם.
מה?
יש סוגיות גם.
נכון.
זה חשוב.
Can I ask you one question?
We miss it
When
and
you
that's
said
it.